Okay, we are recording. So we are in now section 1.4, and we're going to talk about a matrix equation. So right now you have learned about systems of linear equations, and you've learned the row operations to get a system of equations. You write it as an augmented matrix. You row reduce the matrix until you get it in echelon form, and then you can go further and get the augmented matrix in reduced echelon form. And then you can write out the solution to the system of equations if the solution exists. And in section 1, that was really sections 1.1 and 1.2. Section 1.3, you learned about vector equations. And you even saw some applications of vector equations in section 1.3. Now, and you know that a vector equation is really, when you break it down, it represents a system of equations. Now in section 1.4, we work with a matrix equation. And a matrix equation also represents a system of equations. So what I'm doing here is I'm giving just a little example here. Little example where I have a matrix A, and one moment here. One moment. Yeah. Let's see. Let me change this. I got to put in my stylus. Hold on. Let me get my stylus in here. And let me adjust this. 3 point. Okay. So you have here a matrix A, and the matrix A has 3 column vectors: a vector A1, a vector A2, and a vector A3. Those are called column vectors of the matrix A. And what we're doing here is we are going to express, I want to say it the right way, we're just going to multiply the matrix A times the vector X. Now, if I write this here, the matrix A and the vector X, the matrix A has 3 rows and 3 columns. The vector X has 3 rows and 1 column. So really what you're doing here is you're doing a matrix multiplication. Okay, you're taking a 3 by 3 matrix A and multiplying it by 3 by 1 vector X. And since the column number of the matrix A matches the row number of the vector X, then the matrix product is defined. And in fact, that matrix product is going to be a vector B. Well, no, it's just going to be the matrix product. But the matrix product is going to itself be a vector with 3 rows and 1 column. So how do we multiply? I mean, how do we do this? How do we multiply the matrix A times a vector X? Well, we use something called the row vector rule. Now, what is the row vector rule? All right, well, let's look at the first expression here. 2 times x1 plus 3 times x2 plus 4 times x3. How do we get that? Well, what we do is we take the first row of the matrix A, and we take the vector X, and we move along the row and down the column and down the vector and multiply as we go along. So like we have, for instance, 2 times x1. 2 times x1, that's this part right here. And then plus 3 times x2, 3 times x2. That's plus 3 times x2. And then we have 4 times x3. So we have plus 4 times x3. And that's how you multiply the matrix A times the vector x. You move along the row on the matrix A and down the column of the vector x, and you multiply according to this rule. If you notice the second, number here, -1 times x1 plus 5 times x2 plus -3 times x3. Notice what you're doing is you're taking the second row and again multiplying it term by term on the vector x. And similarly with the third row. I mean, are there any questions on this? Are there any questions on what you're seeing here? Are there any questions on this row vector rule, how it works? Okay. Well, if you're good with that, then can we write this matrix product A times X? Can we write it? Well, I mean, we can. I mean, this is a vector. This is it is a. I want to say it the right way. Again, matrix A times a vector X. The matrix A is 3 by 3. The vector X is 3 by 1. And matrix multiplication is defined because the column number of matrix A matches the row number of the vector X. And the resulting matrix that you get is a 3 by 1. And that's what you have here. This is a 3 by 1. 3 rows and 1 column. And we can write this matrix here, this 3 by 1 matrix, as this linear combination of vectors. x1 times that column vector a1, right? That's just the column vector a1 for matrix A, plus x2 times the column vector a2, plus x3 times the column vector a3. Okay, so the matrix A times the vector x, the matrix product, I should say, A times x, is that therefore a linear combination of the column vectors of the matrix A, where the weights on that linear combination are x1, x2, x3. Those are the values of that vector x. So so the vector equation on the right here, this is a vector equation on the right, that equals the matrix equation on the left. And that's one of the key ideas that they try to point out to you in section 1.4. Okay, are there any questions on this? One moment. Okay, sorry about that, class. I had my brother called, but I told him can't talk now. I'm teaching. Okay, so um, let's look at another example here. Let's look at another example. I mean, are there any questions at all about what you're seeing here? All right. Well, if you're good, then let me continue. Let us continue. All right. So let's look at another example here. Now, oddly enough, this example says warm up on it, but it's an example. I wanted to rewrite this. I mean, I don't want it to say warm up. I wanted to say example, but I had to free up disk space on my computer, turns out. So I'll have to worry about this later, fixing that. Hold on. Yeah. Example. Okay, let me give you a moment to copy this example down. Okay, so what we have here are three vectors. We covered 1.3 last week, Cameron. We covered section 1.3 last week. Okay, no problem, no problem. So in this problem here, we have three vectors, and the vectors all live in R3, three-dimensional space, vectors v1, v2, and v3. And you notice when I write a vector, I put a vector symbol above it. Okay, so the way we denote a vector here is this is the vector symbol. Now the textbook, as you know, writes a vector in bold. It's like a bold letter. But, you know, as humans, we'll write a vector with the vector symbol above it. And we want to know if this set of vectors here spans three-dimensional space. Does this set of vectors, v1, v2, v3, span three-dimensional space, R3? That means, can any vector in R3 be written as some linear combination of those three vectors? How many recall spans from their homework? The span section. Okay, good, good, good. Good, Mikhail. Good, Cameron. All right, that was from section, you were introduced to spans of vectors in section 1.3. Okay, so these three vectors, let me just ask you, let me ask you this. Let me sort of take an analogy here. I'm just gonna, I'll come back to this. But if I were to ask, does the set, I guess I should be, does the set I, J, K span R3? Okay, now I is right 1, 0, 0. J is 0, 1, 0. And K is 0, 0, 1. Okay, how many recall seeing IJK maybe in another class, like maybe multivariable calculus, or how many have seen in another class, an engineering class, physics class, IJK vectors? Okay, so David recalls it, Mikhail recalls it. All right, and incidentally, in this class, we denote I1, or I. Oh, okay, no problem. Well, we're going to denote I, J, and K as vectors E1, E2, and E3. Now, in this case, and I believe it was Mikhail who said it, these vectors do span R3. The answer is yes. And the reason is that if you take any vector in R3, you can write it as a linear combination of these three vectors. So like, for instance, if you had the vector -3, 4, and 5. -3, 4, and 5 is -3 times 1, 0, 0, plus 4 times 0, 1, 0, plus 5 times 0, 0, 1. See that? In other words, there is, maybe I'll put this in black. There exists, and let me just check one thing here. Yeah, there exists a linear combination of these vectors I, J, K such that the linear combination of those vectors equals that vector -3, 4, 5. So any vector in R3 you can write as a linear combination of those the vectors I, J, and K, and or we would call it in our class, we would call that that set E1, E2, and E3, and we call that what's called it's a standard basis for R3, standard basis. Now we're asking the same question here when we look at this example that we're looking at. Okay, so I'll go back to the example if that's okay. We're asking the same question. Hold on here. We're asking the same question. Do these three vectors span R3? But of course, it's a little harder to know because just because of the way the vectors are. So let's solve it. Let's see if those vectors span R3. So what we need to do is this. We're going to let the vector B be some random vector in R3. And we wish to see if the vector B can be written as some linear combination of the vectors v1, v2, v3. If it can, if any vector B in R3 can be written as some linear combination of the vectors v1, v2, and v3, then that means that this vector equation here would have a solution x1, x2, x3 for every vector, for any vector B in R3. Okay, so let me give you a moment to copy that. One moment. Okay, so, oh, okay. So, um, all right. So, I want to say this the right way. Having this vector equation, let me just hold on. I want to make sure I'm okay. So that's our vector equation. And if it has a solution, equivalently, we can say that the matrix equation, AX equals B, would, and there it is right there, that matrix equation equivalently would have a solution. And the matrix A is composed of these column vectors, V1 and V2 and V3. That's what the matrix A is composed of. So we want to see if the matrix equation has a solution. So saying the vector equation has a solution is equivalent to saying, does the matrix equation have a solution? And the matrix equation, of course, can be expressed as a system of equations. And that means we're going to do row operations. So you see, we're tying in, there are a lot of ways to understand a system of linear, I'm going to say it's the right way. Hold on, one moment. Yeah, there are a lot of ways to express a system of linear equations. Sometimes you can express it as a vector equation. Sometimes you can express it as a matrix equation. And depending on the situation, sometimes one form is better, is more convenient than another form. So, okay. Are there any questions before we move to the next page? Give me a thumbs up if you're comfortable. Okay, Cameron's comfortable with the material. Marcella's comfortable. Good. Bella and Yassine, excellent. Excellent. Okay, wonderful. Jacob and Mikhail, that's great. That's great. Okay, and Jonathan too. Wonderful. Wonderful. Well, okay, let's go forward then. So now we're going to we're going to try to solve this matrix equation. So what I do is I say, well, let me write the matrix equation as a corresponding system of equations, and then set up the augmented matrix for that system of equations. Okay, let me give you a moment to copy that down, and let me know if you have any questions. Okay, so here we have our system, and we're not really, I mean, hold on here. When we ask, does the set of vectors span R cubed, we're really, I want to say it the right way. I'll write it out. It'll be easier to write it out. One moment. One moment. Hold on here. Let me get the blue here. All right. So I want to say this the right way. Gosh, hold on here. All right. Is this system of equations consistent? If you look at the augmented matrix here, okay, and let's focus right now on the last row. What does the last row say? How would we read the last row there? Right. Okay, Mikhail. Last row, we read it as 4 times something equals B1. 4 times something. Right. 4 times x3 equals B1. This means that, can we solve for x3? Sure. What would x3 equal? Well, you're right. But x3 would equal, that's right, Cameron, x3 would equal B1 over 3. That's right. Or B1 over 4. That's right, Belen. X3 would equal B1 divided by 4. So that means x3, we can solve for x3. And x3 will always be defined for any value of B1 because B1's in the numerator. Okay, so that's not a problem. Not a problem. So we can solve for x3. Now, if we can solve for x3, if we look at the, and let me just, hold on here, so x, 4x3 equals B1. So x3 is B1 over 4. Now, if we look at the second row here, okay, we read that as, right, as negative 3x2 plus 2x3 equals B2, where B2 could be any number. Because remember, the vector B is some vector in R cubed. We have to allow the vector B, the components, to be any components we want. Well, if x3 is equal to B1 over 4, based on the second equation, can we solve for x2? Without any trouble? Yeah, we're back substituting. We can solve for x2. So we'll have x3, x2, and then we can look at the first equation here. First equation is negative 3x1 plus 9x2 minus 6x3 equals B3. And also that equation as well. if we take our x3, our solution for x3 and x2, and back substitute them into the first equation, we'll be able to solve for x1. So we can say this system, without going as far as, well, the system, what form is this augmented matrix in here? This augmented matrix here, right here, yeah, it's in echelon form. And when the matrix is in echelon form, traditionally we are able to test for consistency. And we know this system is consistent. And because the system is consistent, it has a solution. And that means then that there is a solution x1, x2, x3 for any vector b in R cubed. Okay, so system's consistent, and therefore, well, what I just stated is right here. So this means, of course, this means that, hold on here, get this, hold on, where my, hold on, I got to go back for a minute and then go forward. Yeah, okay, good. Okay, so because our system's consistent for all B1, B2, B3, this means then that the vectors V1, V2, and V3, that set of vectors, spans R cubed, Just like the vectors I, j, and k span R cubed, these vectors also span R cubed. Any vector in our three-dimensional space can be written as a linear combination of those vectors V1, V2, V3. That's correct, Mikhail. That's right. That's exactly right. Okay, are there any questions? All right, all right. Well then, I want to just point a few things out in the textbook. So let me go to the textbook here. One moment here. Okay, so here in Theorem 3 from section 1.4, they're just tying together how a matrix equation can be written as a vector equation. Okay, so the matrix equation is like equation 4. That can be written as vector equation 5, and vector equation 5 can be written as the augmented matrix, which we represent the augmented matrix symbolically this way. Okay, so it's just tying things together. And they have some nice examples in the book, for sure. But I think I've hit upon some nice ones actually with you here. But let me just go down a little bit here. Okay, so this is an interesting one here, example 3. There's a matrix A and a vector B, and they want to know, is the equation AX equals B, is it consistent for, hold on, did I lose the book here? Did we go blank? Hold on. All right, one moment. One moment. All right, let me go back here. Sorry. This happens occasionally. Oh, come on. Where's the book? Sorry, class. Just give me one moment here. Just got to get it here. There we go. Okay. So in this problem, example 3, they want to know if, given that matrix A, is the equation AX equals B consistent for all possible values of B? I'm sorry, B1, B2, B3. So it's the same as saying, do the column vectors of that matrix A span three-dimensional space? That's equivalently what they're asking in example 3. If that matrix equation, AX equals B, has a solution for all possible B1, B2, B3, that means any vector in three-dimensional space can be written as a linear combination of the column vectors of the matrix A. So what they do is they say, okay, well, let's see. So they go ahead and they do row reduction. Okay, they do some row reduction here. So like, well, maybe, yeah, maybe I mean, I know what they're doing, but maybe I can be a little more, I mean, if we look here at particularly the second row here, the 0, 14, 10, and B2 plus 4 times B1, how did they get that? Well, they took the first row and they wanted to produce a 0 where the negative 4 is. So using the 1 as a pivot, they multiplied the first row by 4 and added that to the second row, and then that result, that sum was put in the second row. And that's how you got the 0 in the second row, 0, 14, 10, and B2 plus 4, B1, those 4 values. And then similarly, to get a 0 in the first column, third row, you multiply the first row by 3 and add that result to the third row and replace the third row with that sum. And so and then they just continue getting this in echelon form. And when they get there, okay, they get down to here. And they say, okay, well, let's take a look at the last equation. The last equation, okay, all right, they reduce the B3 plus 3 in the third entry in column 4. They reduce B3 plus 3B1 minus 1/2 times the quantity B2 plus 4B1. They reduce that, simplify that to be B1 minus 1/2 2 plus B3. Oh, did I lose the book again? Hold on, let me get it back. All right, I'm sorry about this, class. Okay, one moment. Okay, we're back. Good. Yep. Thank you. So you see, B1, hold on. Okay. So B1 minus 1/2 B2 plus B3, in order for the system to be consistent, well, actually, hold on. I'm going to go to the whiteboard. Let me go to the whiteboard here. Okay, so example 3. Okay, we're looking at the last row. Okay, so the system, and it's an augmented matrix, and I'm not putting in the first two equations, just the last equation. The system is consistent if B1 minus 1/2 B2 plus B3 equals what? That's right, Mikhail. That's right, Bill. It would have to equal 0. Okay, because then the last equation would read like this: 0x1 plus 0x2 plus 0x3 equals 0, and that's okay. That's consistent. So this means that the system is consistent based on only if the B1, B2, B3 coordinates of the vector satisfy this constraint, this condition. They have to, the B1 minus 1/2 B2 plus B3 has to equal 0. Well, that isn't all, not all vectors in R3 are going to have, coordinates B1, B2, B3 that satisfy that constraint, that equation. So this means, and now let me go back to the book here. This means that the system's not consistent. Hold on here. Oh my goodness, hold on. I'm going to investigate this, class. I don't know why the book keeps, there we go. All right. Okay, this means that the matrix equation is not consistent for all possible B1 and B2 and B3. And in fact, the column vectors of the matrix A, okay, the column vectors of the matrix A span a plane in R3 that passes through 0. So you see let me just unhighlight a few things here. The coordinates of the vectors the B1 or the components of the vectors, well, let's say coordinates, because we can think of a vector is equivalently a point, right? So the coordinates of the vectors have to obey the equation b1 minus 1/2 b2 plus b3 equals 0 for the system to be consistent. Well, what's that going to trace out in three-dimensional space? That's going to be an equation of a plane passing through the origin. Okay, that's what it's going to be. It's like think back. If I go to the whiteboard here, like remember in maybe, I don't know, high school or pre-calculus, if you had x minus 1/2 y plus z equals 0, you would say this is an equation of a what? That's an equation of what? X minus 1/2 y plus z equals 0. What does that describe in three-dimensional space? That's an equation of a what's it have to be? That's right, Cameron, a plane. That's an equation of just some plane in three-dimensional space. Okay, how many recall maybe in their high school days studying planes a little bit and seeing equations where you have x, y, and z? Okay, it's been a little while, but you remember it. All right, Cameron. Well, you see what they're doing in example 3 from section 1.4 is they have this restriction on B1, B2, and B3. B1 minus 1/2 B2 plus B3 equals 0. And remember, the vector B consists of coordinates B1, B2, and B3. So this also is an equation of a plane. That's an equation of a plane. And that's what they're drawing. That's what they're drawing in figure 1. They're drawing the equation of that plane. And the column vectors of the matrix A, okay, the A1, A2, and A3, don't span all of R3, but they span a plane passing through the origin. Okay, that's what I'm trying to get across here for example 3. Are there any questions on that? All right. Let me see here. Let me see if I can ask you another question. I don't want everything to be highlighted. Hold on. So the matrix A, they did some row reduction in example 3, and row reduced it to this matrix that I highlighted. Okay. First row is 1, 3, 4. Second row is 0, 14, 10, and the third row is 0, 0, 0. How many? Okay. Does that reduced matrix have a pivot position in every row? No. Good, Bellin. Good, Marcella. The third row does not have a pivot position. So you see there's a tie-in here between the number of pivot positions, and if the matrix equation AX equals B has a solution. This AX equals B for this matrix A did not have a solution, and there's not a pivot position in every row. However, if there were a pivot position in every row, the matrix equation AX equals B would have a solution. Okay, and that's what they're getting at here in theorem 4. Okay, just put a little yellow there. So here it says let A be an M by N matrix. Okay, M by N matrix, M rows, N columns. The following statements are logically equivalent. Okay, statements A, B, C, and D are logically equivalent. So if the matrix equation has a solution, then, for instance, then by part B, every vector in B would be a linear combination of the columns of the matrix A. Then C follows that the columns of the matrix A span Rm space, and D is, then it follows that A has a pivot position in every row. So these are logically equivalent statements. They're either all true or all false. Okay, that's what logically equivalent means. Okay, and you know, this is really these are the key ideas behind section 1.4. Okay, these are the key ideas. Are there any questions at all?
Wait, never mind.
Oh, okay. Okay,
I just wanted to ask for a visual representation of the matrix, but then I realized that would probably take too much time and effort.
So what they're doing, yeah, in example 3 here, let me go back here. Good question. And there, yeah. So for example 3, those, no, let me hold on. Let me get it down a little more. Okay, so in example 3, hold on here. Let me go to the whiteboard. Okay, so in example 3, the matrix A had, let's see, 1, -4, -3, 3, 2, -2, and 4, -6, -7. So this first column is vector A1. This second column is vector A2. And this third column is vector A3. Now these 3 vectors here, this set of vectors, A1, well, we learned that AX equals B is not consistent for all vectors B. It's not consistent for all B. All right. It is consistent. Okay. It is consistent if the, well, I'm going to say, let me say this. These column vectors, A1, A2, A3, span a plane in R3. And that's because AX equals B is consistent if B1 minus 1/2 B2 plus B3 equals 0. In other words, any vector B whose coordinates satisfy this condition, that would make the system AX equals B consistent. But this restriction here is going to cause the vectors that satisfy that restriction are vectors that would lie in a plane. Okay, if you were to find all the possible coordinates that satisfy that condition, that restriction, all the points would form a plane in R3. Okay, that's what it would form. And so that's what they have here. What does that plane look like? Well, here's what the plane looks like in example 3. This is the span of vectors A1, A2, and A3.
Okay, that makes more sense. I think I misinterpreted something as, yeah. Okay, so
Sure.
the plane is the entire span of all through of the whole matrix, right?
It's the span, the plane is the span of those column vectors A1, A2, and A3 of the matrix. But the span is not all of the three-dimensional space. It's a subspace of the three-dimensional space. It's a two-dimensional space shown by that plane. And that plane, the coordinates on that plane would have to satisfy B1 minus 1/2 B2 plus B3 equals 0. All the points on that blue plane in figure 1, the coordinates would have to satisfy the equation B1 minus 1/2 B2 plus B3 equals 0.
Okay. Okay, I think I understand it now. Thank you.
Okay, you're welcome. You're welcome. Very good. Very good. Are there any other good questions? So Belen, it does not span all of R3. Right. Those column vectors A1, A2, and A3 do not span all of R3. In the previous example, the vectors that we had V1, V2, V3 did span all of R3 because we had a consistent system without any restrictions on B1, B2, B3. Absolutely fascinating. How many find this really a fascinating topic? I mean, this tying in the geometry. Okay, Jacob's liking it. Good, good. Mikhail likes it. Good. And any time. See, I love examples where we have like pictures and stuff. It just helps us. It helps us. There's we want to have pictures, right, in our mind of what's going on. All right. Well, on that note, what I want to do is I want to let me go ahead and stop the recording. Excellent.